Hello friends, in this one we're going to do a proof by exhaustion kind of example. So here's a common question. Prove every cube is a multiple of 9, one less than a multiple of 9, or one more than a multiple of 9. That's our objective here. First, let's just do some scratch work to understand what this is saying. So what it's saying as an example is the following, okay? Take a look at these examples. 4 cubed, well that is definitely a cube. That's 64 in other words, but notice that 64 can be written as 9 times 7 plus 1. So this is, in other words, saying that this is one more than a 7th multiple of 9. Look at 5 cubed, that's 125. 125 is the same as 9 times 14 minus 1. This is like saying that we are one less than the 14th multiple of 9. Look at 6 cubed, that's 216, which is 9 times 24. This is the 24th multiple of 9. So each cube that you see in this list, 4 cubed, 5 cubed, 6 cubed, as you can see, is really a multiple of 9. Or one more than a multiple of 9, or one less than a multiple of 9. Keep that in mind. That's what this is saying, and we want to prove this in general. So we can't use numbers for that, because then we would take forever. So instead, let's just use some letters. Okay, so here's an observation that you can make first. Observe that, for example, a number like 1 could be written as 3 times 0 plus 1, because this is 0 plus 1, which is 1. We want to make that observation. Look at the 2. Next number, basically. Notice this is 3 times 1 minus 1, so 3 times 1 is 3, 3 minus 1 is 2. Look at the next part, 3, that's just 3 times 1. So it looks as though 1, 2, 3, and very likely numbers after that could be written as these different combinations of basically multiples of 3 with 1 added, 1 subtracted, or maybe a direct multiple of 3, like this one above my head, which is just 3 times 1 with nothing added or subtracted. So in general, what we can say based on that is the following. Every number n can be written as either 3n plus 1, n equals 3m minus 1, or n just equals 3m. Again, where is that coming from? Look at these numerical examples where it says observe at that line if you have to. Pause and look for that a bit carefully. And if you don't believe it, then extend this. So for example, what if you had to have 4 written this particular form? How would you do that, you see? 5, how could you write that? That would be 3 times 2, which is 6. 6 minus 1, you see? That would give you 5. So you can do some additional cases if this is not enough to convince you. Okay, let's continue. So we're going to make use of this fact that pretty much any number can be written using one of these forms as follows. Take a look. I'm going to prove the first case. The first case basically pretends that n is equal to 3 times m. So what we're going to do is perform a basic operation like cubing both sides. So when I do that, I will have that it's going to be n cubed equals 3m within parentheses cubed. So cube both sides. They're allowed to do that. It's a perfectly fine mathematical operation rather. Now here on the left side, you're just going to have n cubed, but on the right side, that 3 in the exponent has to be distributed to this 3 over here above my head, and also to the m. So when I do that, it's going to give you that n cubed equals 3 cubed times m cubed, but 3 cubed, well, that's just equal to 27. So this becomes n cubed equals 27m cubed. But now we want to really see that this n cubed, which is basically a perfect cube, really is a multiple of 9. So I have 27. That doesn't look like a multiple of 9 until I rewrite it as follows down below. I can also write n cubed equals 9 times 3m cubed, because that 9 is now visible, and 9 times 3 is 27. So I can just separate it into different factors. In other words, what this is telling you clearly is this is a multiple of 9. So be clear on that. You have a 9 in this position. So n cubed equals 9 times some other number, in other words. Whatever the value of m happens to be. So this is telling you that n cubed is a multiple of 9. Next case. Where am I getting these cases? As a reminder, remember that we said either n equals 3m, or n, for example, equals 3m minus 1, or n rather equals 3m plus 1. That's where I'm getting 3 cases. This is also why it's called a proof by exhaustion, because you got to analyze all the cases. So you got to exhaust the possibilities, in other words. Okay, so for case 2, I'm going to take n to be 3m plus 1. Cube both sides. That means I'm going to get here n cubed, and then I'm going to have 3m plus 1 cubed. Now the n cubed part above my head, that's really easy, nothing to be done with that, but 3m plus 1 cubed, that requires a bit of work. So I have to multiply out. I'm going to just show you how to do this. There's a rule for expanding cubes like this. Okay, we can look it up. So in our particular case, what it's telling me is that n cubed will be equal to the following. 27m cubed plus 27m squared plus 9m plus 1. So I basically applied the rule for expanding cubed quantities. So this is a cube of a binomial. 3m plus 1 is a binomial. Now when I look at this expression at this step above my head, I gotta somehow make it look, for example, like a multiple of 9. So I observe again, same as before, that 27, well, that's really 3 times 9, isn't it? That 27 is 3 times 9. Well, that 9m is really like 9 times 1m. So definitely the 9m, 27m squared, and 27m cubed all contain 9 as a factor. So for that reason, you can factor 9 out from each of those terms. So when I do that down below, I'm going to get this result, that n cubed equals 9 outside the parentheses. And then here you have 3m cubed plus 3m squared plus 1m. And at the end, attach that 1. Let's be clear on that. Where is the plus 1 coming from? Back over here, above my head, there's a plus 1. At this step, above my head, you see it doesn't have a 9 in it. So you just have to keep that separate from the terms that like 9m, 27m squared, and 27m cubed. So down below, if you look at this very carefully, what it's really telling you is that you have 9, then you have some expression within parentheses, and then you have plus 1. But if you think about it carefully, this is saying it's a multiple of 9 plus 1. In other words, what it's saying is that we have proved essentially this part right here. See where it says 1 more than a multiple of 9. You've proved that part. Just like the case 1 proved that every perfect cube is a multiple of 9. The third case is to prove that 1 less than a multiple of 9. Now let's do the last case, so case number 3 basically. What I have is that n equals 3m minus 1. Now if I cube both sides, that's going to give me n cubed equals 3 minus 1 cubed. Expand 3 minus 1. So in other words, multiply it out if you like. That's going to give you that n cubed from the left side equals 27m cubed minus 27m squared plus 9m minus 1. Again, observe that. 27m cubed has 9 as a factor. Negative 27m squared has 9 as a factor. 9m has 9 as a factor. But that negative 1 doesn't, so you just keep it. So this allows you then to do after that is factor 9 from each term that has 9 as a factor. So then all the way on the bottom, essentially I will say that 9, or rather n cubed equals 9 multiplying 3m cubed minus 3m squared plus 1m minus 1 at the end. But really, what this says is that we have a multiple of 9 minus 1. The 9 is outside of parentheses. That whole expression within the parentheses, if you plug in different values of m, is really just a number, you see? So in other words, this is a multiple of 9, and then at the end you have that minus 1 attached. So this has proved this case right here, that 1 less than a multiple of 9 also holds. And that's it. This is the entire proof. All the cases have been exhausted. Thank you so much. Please leave a like and subscribe. I hope this has been helpful and insightful. I've tried to annotate everything as clearly as possible.